Hello and welcome to everyone on the call. Thank you for joining us today, where we shall be looking at how to use the open source machine learning toolkit Kubeflow in conjunction with the Elastic Kubernetes Service EKS and the Elastic File System EFS. My name is Stuart Scott. I'm the AWS Content Director here at Cloud Academy, and today we are very lucky to be joined by Suman Debnath, who works for AWS as an AWS Principal Developer Advocate. However, before I hand over to Suman, I just want to let everyone know that this session is being recorded and you'll receive a copy of it shortly after this webinar. Also, if you have any questions, then please use the question box available. And when we get towards the end of the presentation, we shall have some time where Suman can answer these questions for you. Also, as we close out the webinar, there'll be a brief survey, and we truly appreciate your time and effort in filling this out, as your feedback helps us to improve any future webinars that we host. So let me now hand over the reins so we can get into the meat of this session, which I believe is going to include a demo, which is always super helpful when explaining how to configure components in AWS. So over to you, Suman.
Hello everyone, welcome to this session on machine learning at scale using Kubeflow with Amazon EKS and Amazon EFS. My name is Suman Debnath. I'm a developer advocate with the EFS product team, and I'm super excited to share a few of the insights about how you can run your machine learning workflow using an open source tool called Kubeflow. What we are going to do in next 30 minutes or so, we are going to talk about why machine learning on containers, because that might be little odd to many of you if you are new to container space. And we will then dive a little bit around Kubeflow, and then we will straight away jump into the demo, which is more interesting rather than these boring slides. So first thing first, why machine learning with containers? So if you think about it, it's not only about machine learning. We get the flexibility and all the benefits that any application can get with containers. So if you look at the whole machine learning stack, there are different tools like TensorFlow, PyTorch, and we need different kinds of infrastructure to run this training. So things gets very complicated when you think about different packages, dependencies, and configurations. So what containers helps us to do is, it packages our training code along with all the dependency in a much modular way. And that way, our ML environment gets very lightweighted, and it's very much gets portable, right? So you can run your machine learning training jobs or other tasks, independent of the platform. So one of the reasons that why it is even better to run it on Kubernetes is, first is composability. So basically, you are defining your training jobs, or you are defining your machine learning task in a granular way, and so that you can always run it at different places. And if you want to make some changes, it doesn't affect the other jobs in your pipeline. The other thing is, you can start today on-prem in your Kubernetes environment, and you don't have to change it in future if you want to migrate it to AWS and run the same training job on the cloud. So since it is created as a container on Kubernetes, it gets very much portable, as we have just discussed a while back. And obviously, you don't have to think about the scale because Kubernetes will take care of the infrastructure. So whether you need 2 instances to run the training job, or 3 instances, or 10 instances, since the training job is running as a container, you don't have to worry about the backend infrastructure, which is very much valuable for any machine learning engineer, or even for any infrastructure engineer. And the best part about this is you don't have to worry about managing this Kubernetes cluster. So you may like to use Amazon EKS, which is our managed Kubernetes service on AWS, which helps you to give you the control plane where you can attach your data plane or compute nodes. and it supports you can always get your Kubernetes upstream experience, and you can decide which version of Kubernetes you want, but you can natively get the upstream Kubernetes experience. So it will look it will feel exactly the same as how it is if you have to install and configure Kubernetes on-prem or in your managed EC2 instances. And it gets integrated with a lot of other AWS services, and which we are going to see in a while, where we are going to run machine learning job using Kubeflow on EKS, and we are going to save our training data sets on EFS. And one of the other thing is, irrespective of Kubernetes, is you don't have to build all those training container images from scratch. So we do offer a lot of pre-packaged Docker container images, which are fully configured and validated and tested rigorously. So you are always get the best configuration and image which you can make use of. So you can just, what you can do is you can just create your own training script, or use the training scripts that we have as a template, and make the relevant changes based on your need and requirement. You can always customize those container images, and we support different frameworks like TensorFlow, MXNet, PyTorch, and so on. And the best part is, you can use these deep learning containers not only with EKS, but with ECS, Amazon SageMaker, and EC2 instances. So let's talk a little bit about Kubeflow before we jump into the demo. So Kubeflow is basically, you can think of it as a machine learning toolkit for Kubernetes. So it comprises of various other projects like Jupyter Notebook, pipeline, training services, and inference, or serving. So basically, if you have ever seen Amazon SageMaker, it's kind of a similar platform that you will get here. It may not have all those fancy features that SageMaker offers, but if you want to run your machine learning workflow on Kubernetes, and if you want to have a control over your workflow even at a more granular level, then maybe you can make use of Kubeflow. And it's an open source project, so you can always contribute to that. And we are going to see in the demo that how you can create a Jupyter notebook, and how you can start a training job on Kubeflow. Now, one important advantage of using Kubeflow on AWS is you are going to get a lot of flexibilities and leverage the integration that AWS has with other services. So when you are running Kubeflow on EKS, you get all the goodness of the service integration that we have with EKS. So in this case, we are going to use EFS with Kubeflow, but if you see here, we have a good ecosystem where you can integrate other managed services that we have for better experience for your machine learning workflow when you are running on Kubeflow. So since we are going to use EFS in our workflow, so let's talk about EFS a little bit, right? Because we learned a little bit about EKS, which is a managed service for Kubernetes. So let's spend a couple of minutes on EFS. So EFS is a simple serverless and set and forget kind of file system, which you just create it, and you don't have to mention the size of the file system, and you can just use it anywhere. So you can access that file system from your on-premise a machine, or you can access it from EC2 instance, from a Lambda function, or from a Kubernetes cluster. And we are going to use EFS for saving the training data set for our machine learning workflow. But it's very much elastic and performant. We recently announced a sub-millisecond read latency. So that means in general, you will get a latency of 600 microseconds for your read workload, which is pretty amazing when you think about shared file system on the cloud. And it's highly available and durable, and we have different classes of storage that you can select from. So as we discussed, EFS has an integration with, you can access EFS from various different compute services. So one is on-prem or EC2, but we don't stop it there. You can always use EFS with any of your containers which are running on ECS, which is our managed container service, or on EKS, which we are going to use, in our demo. So how to get started with the EFS with Kubernetes. So now we are not talking about Kubeflow in general because we are going to do that in the demo, but I just want to give you an overview of how you can get started with EFS with Kubernetes. So the first thing is you need a Kubernetes cluster. So in this case, we are creating an Amazon EKS cluster, but this could be very much your own installation of Kubernetes on a bunch of EC2 instances where you are managing the Kubernetes cluster. But we are just taking this example where we are creating a managed EKS cluster. What that means is you don't have to manage the cluster by yourself. All the patching, version control, and all of that updates is taken care by Amazon. So first you need to create that EKS cluster, and second is you need to create a security group so that the EFS file system can be accessed from the EKS cluster, and then you have to create an EFS file system. Now we are going to do this through the code in a while, but this is how the workflow would look like. And the most important thing is you need to install the EFS CSI driver. This storage driver doesn't come out of the box. So once you have your EKS cluster, if you want to attach EFS storage, you need to install this CSI driver, right? So this is also an open source project. If you would like to contribute, feel free to contribute on this project. It's we have done a lot of improvements in our CSI driver in the recent past, so please have a look. So once you have created this EKS cluster, you have created the file system, and you have installed the CSI driver on the EKS cluster, what you can do is you can define a storage class, right? So in the storage class definition, you will provide that file system ID, which we have just created, and that's all, right? So after this, you can run your application by creating a persistent volume claim, and you will define the same storage class which you have used before. So here, if you see the storage class name that we have given is EFS-SC, you just refer to the same storage class in your PVC definition. And once that is done, you can mount that PVC in your application or in your pod, right? So in this case, we are just using the same persistent volume claim whose name is EFS claim. And if you see this is the same claim name that we have used to create this PVC. So that's all. So next time, if you want to run another application, you will just create another PVC and use it in your pod. So you don't have to go back to storage over and again, right? So because we are using dynamic provisioning, and the CSI driver will take care of creating those access points, which is the technology behind provisioning these PVCs, right? So that's about how you a little bit about how you can make use of EFS with Kubernetes. So before we jump into the demo, this is what the architecture of our demo. So we are going to use EFS to storing our training data set. So in our demo, we are going to download the training data set and we are going to run some training job on Kubeflow, and that training job is going to access the storage from EFS using the CSI driver. And for our training job, we are going to build an image and then we will push it to ECR, which is our container registry, which is kind of Docker Hub, but it's within AWS. And then we will start the training job on our EKS cluster using Kubeflow, and it is going to pull the image from ECR, run the training job on the training dataset, which is saved in EFS. Okay, so let's jump into the demo and see it all in action. Okay, so I have already opened my AWS console, and if you see, I am inside Cloud9. So we are going to use Cloud9, which is an IDE for writing your code on AWS. So it will give you a nice IDE kind of environment which runs on an EC2 instance, but it's very easy for you to write code as you go along. You don't have the dependency to carry your laptop or workstation. You can just write your code from anywhere as long as you have the internet connectivity. So if you come here, and you can see that I have two environments. So I have already opened this environment. You can always create your own environment by clicking on create environment, and it will ask you just a few questions: what type of EC2 instance you need, what operating system, and you are all set. So this is the IDE environment that I have. If you come here and click on Open IDE, you will land onto this page. So I have a lot of code here. I have cloned few of the GitHub repo, which I'm going to share in a while, but you will get this kind of interface. Okay, so first thing first. So I already have an Kubernetes cluster up and running, and we can see that if you run kubectl get nodes, and we have an EKS cluster with 5 nodes. I have also installed Kubeflow, and if you want to see that, we can see all the pods running as part of Kubeflow, because Kubeflow, as we have learned a while back, it's a collection of different services, right? So we have all those pods running, which supports which are actually running Kubeflow. So the first thing is we need to create an EFS file system. At this point, we don't have any EFS file system created. And if you see kubectl get storage class, or SC, you see that the default storage, which is an EBS volume, which is by default when you create an Kubernetes cluster on AWS. Now, the first thing we need to do is we need to create the EFS file system, and then install the driver and create a storage class. So we don't have to do it all manually. We have created a script which is located inside this directory, and it has some dependencies. So if you see this, auto EFS setup of script, we have some we are using some external libraries. So for that, we have one requirement.txt file. So first, let's install all the packages. So I have it installed, so it will just skip all of the installation. So next is we need to run this script. So let me just run this script, and then we can go over what the script is doing. So before I hit enter, I just want to show you a few parameters that we are passing along. One is the region. That means in which region we are creating this file system, which is obviously in the same region where I have my EKS cluster. So I'm just giving the cluster name, which I've saved in the environmental variable, and then the file system name, right? So before I hit enter, if you come to EFS console, and if I hit refresh, we see that there is no file system. So hopefully after this script gets executed, we will have a new file system. So by the time this runs, let me just quickly show you what the script is doing. So if you see, the script is doing just 3 basic things. One is it is checking few of the prerequisites and what is needed, and then it is creating the IAM role so that the cluster can access the EFS file system. Then it is going to install that CSI driver, which we just talked about in the presentation, that it need to install the CSI driver so that the Kubernetes cluster can talk to EFS. And then we are just creating a file system, and after that we are creating a storage class. And this is the storage class which we are going to use in the Kubeflow for training our job, or even for the notebooks, to creating different data stores for keeping our training data sets. Okay, so creating a file system and creating a storage class is something that you can repetitively do as and when you need, but this setting up the CSI driver and all of that is just one-time activity. So it will take a couple of minutes, so let's wait for this to complete. Okay, as we can see, it has created a file system. Also, it has created the mount targets, and it has provisioned a storage class. So to see that, we can just run kubectl get sc. So we can see that there's the storage class which has been created, right? And it is still not the default one. So if you create anything on Kubeflow, let's say Jupyter Notebook, it will use this storage, but if you explicitly mention this storage class, it will carve out storage from here. Okay, so now before we go ahead, if we go to EFS and click on refresh, you will see that the file system got created, my EFS1, and this is exactly the name that we have given while parsing the EFS file system name in the script. So we are all good now, and if we come inside this file system and come to access point, which is the entry point for the application to EFS, you see that there is no access point created because we have just created the storage class, but there is no PVC we have claimed or created. So the next thing would be, let's go ahead and create a Jupyter notebook. So to do so, first we need to run I think it's already running, but let me just stop and start it again. So this is the dashboard service, or basically Estilo service. And now if I just go to preview and open the app in a separate, not here maybe. So I'm just closing this off and going back here. So now the dashboard is up and running, and we can see that here. And if you see here, we have notebook, TensorBoard, volumes, and all of that, pipelines, everything. So this is kind of if you have seen SageMaker on AWS, it's kind of same, but it has SageMaker has a lot of different flexibility and features, but this is kind of a nice environment for you to manage inside out. So you have more granularity, and it's all running on Kubernetes, which is great. So now if you see here, we don't have any volume. So let's create a volume, and this is the volume which we are going to use for keeping our training data set. So let's give some name, and let's give some size, let's say 100 GB. And here we can select the storage class, and we can have access mode as maybe read write many, which EFS supports. That means you can access this volume from multiple pods. So let's create it, and it is going to be in pending state because we have not yet attached this volume to any of the Jupyter notebook or any of the other training jobs. So let's go ahead and create a Jupyter notebook. Let's give some name. Let's say notebook 1, and here we can select the image, but let it be the default, and it is going to create a volume for its own use, basically the home directory for this notebook. And since our default storage class is EBS, so it is going to create that PVC from this storage volume or GP2 type of storage class, but we are going to attach one external volume, which is going to be the dataset EFS volume, which we have just created. So let's attach this and click on launch. So if you see, it's already got created, and if I come to volume now, you will see that the data set is also, the status is now bonded. And we also have another volume, which is for the home directory, and this is coming from GP2. And now if I come to EFS and click on refresh here, you will see one access point which got created dynamically by the CSI driver. So let's go back to our notebook and connect to our notebook. And what we are going to do now is we are going to run a training job, but before that we need to have some data set, right? So what we are going to do is we are going to create a Jupyter notebook, and we are going to download some data set. So I already have the location of the data set, and it is basically a simple data set which contains images of different flowers, and what we are going to do is we will run a CNN job, or basically a deep learning a training job, which will identify the type of flowers, given an image of a flower. So this is a very tiny training data set, and the focus is not on machine learning part, but the idea is, what I really want to give you is how you can make use of Kubeflow to run your training jobs. So if you get inside this data set, and this data set is coming from the EFS storage, if you uh, get inside this, you will see different types of flowers: rose, sunflower, and so on. So let's wait for this to get downloaded, and once this is over, what we will do is we will go to Kubeflow and start a training job. So as you can see, the training dataset has been downloaded, and we have images saved inside this EFS dataset share, right? So we are all good to start the training job. So let me close this Jupyter notebook, because we don't need that. The only thing we wanted to do is to download the dataset, which is now stored in in this EFS file system via this access point. So now let's go back to our console, and let's start the training job. So just to recap, where are we now? If we open this architecture, we have saved the training dataset on EFS, and all we need to do is run this training job. And for this, I already created a deep learning image which contains the code for running that training job, and we have to build it locally on Cloud9 instance, and then I pushed it to ECR repository, which I'm going to show you. And then we can simply go ahead and run a training job on Kubeflow, where I have specified the training dataset location as the dataset which we have created, and the image to use is the same image which is in ECR, right? So let me show you the image first. So if we run docker image ls, you will see that we have one image, or a repository inside that we have this image saved, and all this code, like all the docker file for this, it's there in the GitHub repo, which I'm going to share with you towards the end. But if you want to quickly look into the docker file, it's simply we are just pulling one TensorFlow base image. We are copying this training script which is located here, and we are just giving this as an entry point. That's all. It's nothing fancy. And inside this training script, we are running that machine learning training. So let's go to ECR, and this is my repository, my repo. And if you see here, this is the same repository right in my account, and inside that we have our image, right? This is the image that we are going to use. So let's run it. So the training job is basically we are going to run on Kubeflow. So it's also defined as a YAML file. So this is inside this notebooks, inside this 1 second. Yeah, inside this training samples in the tf job.yaml. So if I just open this up, you will see this is a TensorFlow job. This is the name of the job, and we are going to create 2 replicas. That means when we execute this, you will see 2 pods getting created for this training job. And if you see here, this is the image we are using, and the most important part, the training dataset, because this training will be running on some dataset, right? And this is the same dataset which we have downloaded a while back inside this dataset PVC. So if we run this kubectl get PVC, let me just grab the namespace. if you see this, this is the dataset PVC, and this is the same PVC which we are mounting on this uh, training job, right? So this training job is going to create a pod, right? And that pod will have our EFS storage attached and mounted, and it will be mounted inside this train directory. And in our training script, we have mentioned that go and read this directory for your training job. So let me open this training.py, and if you see it here, we are mentioning where is our training dataset located. Okay, so let me go back to our CLI and let's run this job. So we are inside this ML folder, and the training job is inside this training samples directory. So we can simply run this kubectl apply and the training, and the location of our definition file. So now if we see the training job, it is now in the pod creation phase. It is yet to start the training, but we see that there are two pods which it created. So we can even run kubectl get pod -n the namespace, and you will see that these are the two pods which are running, and these are the exact same two pods which we name that we have given image classification PVC. So it's worker 0 and worker 1 because the replica is 2. So now what we can do is we can even see the logs by getting into one of these workers. Right, so let's run this, and if you see, the training job is already completed because it was a tiny data set, and we just ran it for 2 epochs. And if you see that the accuracy is not at all great, but that's okay. So the idea is basically to show you how you can make use of Kubeflow to run your training job without any hindrance. So our training job got over, and now if you see the pods, you see that it's in not ready state. I mean, meaning it's not running now, so it's already over. And what we can do is we can even delete this whole deployment. So by just we can just copy this, and maybe to delete this job we can just say delete, and let's copy this and run it, right? So if you see here, what Kubeflow allows us to do is it allows us to scale our machine learning workflow dynamically. So we don't have to worry about the infrastructure that is needed for your ML training, right? And with EFS you get the flexibility to attach or use the storage for your team, for different data scientists, or maybe for different users, saving your training data set in one central location, which can be accessed by different people, right? So if you see here in the EFS, this is the place where I have my training dataset. So you can not only access this from your Kubeflow users, but also you can, let's say for troubleshooting, you want to attach this to an EC2 instance and want to explore something. So maybe you want to see what the training dataset is for some ad hoc task. So you can always click on attach and copy this command and mount this file system as an NFS storage into your EC2 instance, provided that you have all the permissions granted. So the idea here is when you use EFS, the same storage you can access from containers, from your EC2 instances, Lambda functions, and all of that, which gives you a lot of flexibility. Right. So, and you don't have to provision it beforehand. So if you see here, nowhere we mentioned the size of the file system, right? So it will scale up and scale down, automatically. Although when we created this volume, we mentioned this size just to make Kubernetes happy, because for Kubeflow or for Kubernetes in general, you need to mention the size of the PVCs. But that is not from the EKS standpoint or from EFS standpoint. It is just ignored because there is no requirement for size, right? So that's all about it. And if you want to go through this whole demo, this is the location. So you can get into Amazon EFS developer zone. Inside that, we have a machine learning with Kubeflow, on EKS with EFS section. And this is this tutorial will guide you through setting up the whole environment on Cloud9, and also the training job and few other things. So if you want to try out, feel free to go over here and give it a try. And to come to this page, you can go into this landing page, Amazon EFS developer zone, and if you scroll down, you will get some information about EFS, like what it is, how it works, in a little bit of details. And if you scroll down, you will see a section of different integration. So this is Amazon EFS with containers, and here you can see machine learning at scale using Kubeflow. So you can always click here and you will go to that page which we have just seen, and do it in your account. Okay, so that's about it. So let's go back to our slide. All right, so now that you've learned a little bit about how you can make use of EFS with EKS for Kubeflow, there are plenty of other Kubernetes or container specific tutorials which are available on Amazon EFS developer zone, which we have just seen a while back during the demo. But feel free to access this page and share your experience. And if you would like to contribute, maybe you can send a PR request with your demo, and we will add that in the repository.
Thank you very much for that great presentation and demo there, Suman. We've had a few questions come in, so let's take a look at those questions. So firstly, I've got a question here. Can we use any other storage service apart from EFS in this architecture?
Yeah, sure. So I think we can make use of different file systems that we have on AWS. So one of them is surely you can use S3, which is our object-based storage, just like how you use S3 from Lambda or from any compute service. But when it comes to file system, either you may like to use EFS or FSX for Lustre. So if you have a performance intensive, machine learning model, which requires a very high throughput, although EFS also supports very high throughput and performance, with the latest release of sub-millisecond read latency, but just in case you want to have some machine learning model which is performance hungry, then you may like to use FSX or Lustre. And
Sure.
FSX CSI driver is also available for anyone to use. So just like how we used the EFS CSI driver, one can use the FSX CSI driver to attach that volume.
Okay, excellent. We've also have another question here. Why do we need to mention the size of the volume while creating the PVC, even though EFS is elastic?
Yeah, I think that's a very common question we always get. And the reason is, as we just saw in the demo, the size is a construct of Kubernetes. So when we create a persistent volume claim, we need to provide size as per the specification of Kubernetes. So it's not specific to EFS. So we need to provide that size. That is what the manifest says. And now in our case, we are using EFS as the backend storage. So it could be EBS or some other storage on-prem or whatever. Now, depending on the backend storage technology, different products and services can handle that. So for EFS, as it is a file system which is completely elastic, where you don't have to specify the size, we just ignore that. So we don't, you are specifying this just to make Kubernetes happy, but from EFS standpoint, we just simply ignore.
Excellent, thank you. We've got another couple of questions here. How can we set this environment and deploy the same in our account? And where can I get the code?
Yeah, sure. So I think we shared that GitHub link. It's under AWS samples, you can search for Amazon EFS developer zone. So you can clone that repo, and it contains this whole workflow, the demo that we showcased. Although we started off with the EKS cluster up and running, but that GitHub page will walk you through all the steps, starting from setting up the Cloud9 instance, so that you can run it through in your environment from scratch, and then based on your need and requirement, you can change things and play around. So all the code is there, in the GitHub repo.
Excellent, thank you. And we've just got a question coming here. Did each pod train on a separate subset of the data and combine the results, or did each pod run on full set of data?
Yeah, that's a good question. So when we attach the EFS file system to Kubeflow, or in this case for the training job, we had two training pods, right? And they all have the access to the same data set. So what Kubeflow will do is it will divide the workload, and it will train it parallelly across both the pods for the same data set, but they will read the different set of data in that data set, but they both the pods will have the access to the same file system. In fact, if you look at those two pods might be not might it would be running on two different EC2 instances if your cluster is having more than two instances. In our case, in the demo, we used 5 instances in the EKS cluster. So those two training jobs were running literally on two different EC2 instances, and those two EC2 instances were accessing the same EFS file system. So it's all taken care by Kubeflow internally, but from infrastructure standpoint, it's the same data which is getting accessed by both the pods.
Great, thank you very much. I just had one final question come in. Would EFS automatically scale even if in the beginning we provided vol constraint of 100 gig? If the training data goes over 100 gig, would we face any issues?
Yeah, that's a good question. So I have personally have not tested this. I'll surely do that. But from the storage standpoint, from EFS, if you look at it, we don't have any cap on the storage. So because at the end of the day, for EFS, it is completely blind that whether the IO is coming from EC2 instance as a raw IO, or it is coming from a compute, or whether it is coming from whether it is coming from EC2 instance, or let's say serverless compute like Lambda or EKS or ECS. But now when you define 100 gig at the Kubernetes side, if Kubernetes have a restriction and check the size of the volume, then it might throw error. But from EFS standpoint, it will just let it go. So it is just an basically you can think of it as a administrative parameter where you can see where you can just monitor how much capacity every application is entitled to have.
Great, thanks very much, Simon. Well, it looks like we've come to the end of the questions. So I just want to thank everyone for joining today. I hope you managed to take something valuable from this session. And don't forget, if you want to take a look at both past and upcoming webinars Cloud Academy is hosting, then take a look at cloudacademy.com/webinars. And just as a gentle reminder, there will be a brief survey when the session closes, and we'd really appreciate any feedback you have. So thank you again to yourself, Suman. I really appreciate you taking the time out to talk with us today, and hopefully we can do it again sometime soon. Do you have any closing remarks for us and the audience before you go?
Yeah, sure. So thank you so much, Scott, for giving me this opportunity. It's really a pleasure to be with you and Cloud Academy, and I look forward for many more webinars and maybe hands-on workshop in the upcoming days. And I would like to thank each and everyone who joined this webinar. Thanks so much for your time during the work day, maybe in the middle of the work day. And I look forward to hear feedback from you. And if you have any questions or queries, feel free to reach out to me over LinkedIn or Twitter, whichever you are comfortable with. And it's not about this demo, but I just want to make sure that we connect with each other, and we can learn from each other. And I'll do my best to help you build what you are working on or what you are passionate about on the cloud and on AWS. So thank you so much for your time.
Yeah, thank you very much, and I really appreciate all of that. So I think that's brought us to the end. So thanks again, and goodbye, and hope to speak to you all again soon. Cheers. Thanks very much.
Thank you. Bye.